the class, we're going to use our knowledge of derivatives to solve problems that involve exponential functions, one of which we started yesterday. And so we already know that the initial population of rabbits of this thing is when you put 0 into the function and you get 800 rabbits. So we already know that. We also knew that if I want to know how many rabbits there are after 14 days, there's no calculus involved in that, folks. I'm just going to simply put 2 into the function for t, and it's going to be approximately 939 rabbits. What we didn't get to, and what we do need to talk about today, is what is the rate of change of rabbits after 14 days? Well, as I said, I want to get through this fairly quickly. So I'm not going to sort of stop and sort of ask the questions I normally ask as I go through this. I want to be sure I get through the other 2 things that I want to do, right, before the end of the class, and then even have time for the group assignment that I want you to do. So I'm just going to say that if we want to know the rate of change after 14 days, we're going to clearly need a derivative for that, right? How are the population of rabbits changing over time? That's what we're asking. So after 14 days, again, would be a t of 2. So the first thing I'm going to do is I'm going to find the p of t, and I did that right here. That's something you're supposed to be able to do fairly well at this point. So leave that 800 out of it. I always like to say if there's a coefficient, just kind of put that at the end. So it's going to be e to the power of 0.08 to the power of 2. And then, e to the power of 0.08 times, sorry, I'm looking at the wrong thing, down here. So here's my derivative, right? If you just follow through, you should be able to get that derivative fairly easily. And then it works out that when you put 2 into that, you get 75.1. What does that 75.1 mean? That's a rate, right? That's a rate when you're at 2 weeks or 14 days. And that 75.1 means it has to be expressed as a rate of 75 rabbits per week. And because it's positive, it means that the population is growing. It's increasing at that rate, 75 rabbits per week, all right? And hopefully that makes sense. So let me go ahead and do a question similar to one that we did in class. And I thought of, sort of throwing it out to the class and getting you to do it, but I have other questions on the whiteboard that I want you to do. So let's just do this one together. You're investing $2,000 in an account that pays 12% per year compounded quarterly. We didn't do quarterly in the last question. We did compounded annually. And at any rate, let's just theoretically talk about 12% as the rate that you're getting compounded quarterly. Now, if you remember what quarterly means, it means 4 times a year. So it means that you're not going to get 12% 4 times a year. You're going to split that up into 4. So here's what the equation looks like. So the 2,000 is your principal, and it's 1 plus the rate expressed as a decimal divided by 4. Then you're going to multiply 4 times the t. Okay, that's how we do this. So this is how we would actually, and why 4 times the t? Because remember, you're getting paid 4 times a year. So that's why it's 4 times the t, right? So you divide by the 4 and you multiply by the 4 up here. And t, of course, represents the number of years. Why did we have 1 plus? That is the actual formula for compound interest. Can you explain each part of the equation again? Okay, so let me grab my stylus here for a second and just remind you that, move this out of the way, generally for compound interest, I'm writing out the compound interest formula now. The compound interest formula says that A is equal to the P, which is the principal, 1 plus what's called periodic interest rate to the power of n, where n represents the number of compounding periods. Okay, how many times did you get paid? Basically, I tell you that the finance unit is my favorite unit. So the I here is not the annual interest rate, right? It's the interest rate per compounding period. So if there are 4 compounding periods, in this case it's quarterly, then what I'm going to have to do is I'm going to divide the 12%. 12 expressed as a decimal is 0.12. I'm going to have to divide that by 4. And then because I'm being paid 4 times for the year, it's going to be not just n, but 4 times t. So if t is 3 years, here's what we're saying. If you're doing this for 3 years, you're going to be paid 12 times because it's 4 times per year. And that's where the 4t comes from. So we're dividing by 4 because you're taking 1/4 of the interest each time you get paid. But then you're going to get paid 4 times, so it's going to be 4 times t. All right. So does that, Taj and Kushi, make sense? That's just a formula for, you're welcome. That's just a formula for compound interest. All right. That's something you'd have done. I know that was a while back. That was grade 11. That's the formula for compound interest. The I here is not just interest rate, it's the interest rate compound per compounding period. If this was that I was being compounded monthly, I divide this 0.12 by 12. Then I multiply this by 12 up here as well. At any rate, I've simplified this to 2001.03 to the power of 14. Okay? All right. So the question is, how fast is his money growing 3 years into his investment? And how much money does he have at this point? So how fast he's growing means I have to figure out, first of all, what my derivative is. And there's my derivative. That's my A of t. Again, I'm expecting you to be able to do this derivative, right? Remember, the base of the function is 1.03. So that's why I have the ln 1.03 here. And then I'm going to take the 2000 times 1.03 to the power of 14 multiplied by the 4, because that's a derivative of the exponent here, which is what this is. And then I can simplify that sum to make it look like that. So the question now is, how fast is it growing in 3 years, or at year 3? We're just simply going to put 3 into the derivative. And it says that our money is growing at $337.15 per year in year 3, or at year 3. So at the 3-year mark, that's how much his money is growing by, right? His $500, sorry, $2,000. His $2,000 is growing at a rate of $337 per year at the 3-year mark. Does that mean that in year 4 it's going to be growing at that rate? No. The way compound interest works is that every year the rate that you're going to be growing at is in fact increasing. If this was simple interest, that would not be the case. For simple interest, your money grows at the same rate every single year. But compound interest is different. Compound interest is powerful, right? Remember that when you're investing, by the way. Compound interest is powerful because your rate of growth is actually growing itself. So in year 3, you're growing at a rate of 337.15 per year. By the time you get to year 5, 6, 7, or 8, your rate of growth is actually higher. Okay, so the next part of this question is, when is this money growing at $500 per year? Well, set this equal to 500, because that's what I'm trying to. It's similar to the question I did with you a couple of days ago, where we talked about the $1 million and we wanted to know when it was going to be growing at $100,000 per year. What we did is we set the derivative equal to 100. Well, it's the same thing here, right? When is this money growing at $500 per year? Set the derivative that we had from the previous line up here, set that equal to 500. And now we have to solve for t. The process is simple. I'm going to just divide through the 500 by the 8,000 times ln of 1.03. All right. And then I'm going to take the log of the two sides. And I chose ln, not that I had to use ln. I've said this before. You could use a log base 10, right, as long as you're using the same log on both sides. But some people might think, you're already using ln in the equation. Why don't you just keep using ln all the way? So here's my ln right here of the two sides of the equation, which allows me now to put the 4t in the front, right? And then I can go ahead and make t equal to this thing over here. And I'm going fairly quickly, but you can always go back and look at the video, slow it down, pause it, whatever you like, to review what I'm doing. I'm trying to solve for t, and that would be the algebra involved in solving for t. So what does this work out to? It works out to be 6.3. So in 6.3 years, his money grows not at $337.15 anymore. That's year 3. By the time you get to year 6.3, it's now growing at the rate of $500 per year. I already made the point that over time, your money grows faster and faster and faster with compound interest. The higher the interest rate is, the faster it grows. 12%, I'm going to repeat, is not realistic in the current environment. But that has nothing to do with this. We're just sticking to the numbers and saying, what if it was 12%? What would happen? And that's what would happen. Okay, moving on to the second question. A certain population of squirrels is represented by this function, and I give you an equation where p is the number of squirrels measured in hundreds after t weeks. So I'm monitoring the chat as I go along. And please, if at any point, and I'm glad that people like Kushi and Tara said, whoa, hold on, let's just review the equation again. So as I go through this, anytime that you're not sure about anything, then you need to stop me. All right, this equation is given. So this is not like this is based on, some pre-existing population growth function, right? That's just given to you as part of the question. But they're saying that this squirrel population, the, the number of squirrels is represented by this. So 4 times t e to the minus 5t, minus 0.5t. So in hundreds of squirrels, by the way, after t weeks. Determine the function which represents the rate of change of squirrels. Well, a rate of change function is a derivative. So the first thing we're going to do for part A is to find the derivative of this function. And again, I'm going fairly quickly here because I would think that you would know how to do this. This is a product of two functions. Think of it as a product of 4t and e to the minus 0.5t. So I dealt with this as a product when I was deriving it. And get your practice with this as much as you need to. It works out to be this in the long run. Okay? So that's the function that represents the rate of change. After how many weeks is there a maximum number of squirrels present? So I'm thinking, how can I figure out where this thing reaches a maximum? Can I get some feedback from you on that? Right? If what I'm trying to do is figure out where this thing reaches a maximum, and I have the derivative, we've done maximization and optimization before in this course. What am I going to do with this in order to be able to figure that out? Thank you, Sarah. Thank you very much. Only one response, but thank you. It's the right response. Set the derivative equal to 0. So I'm going to do that. Right? So I'm going to, by the way, this is the simplified version of the function by factoring. And that's something you want to make sure you're doing as much as possible when when one of your goals is to set it equal to 0. So here's where I factored it, right? Look at what I had before and see that the common factor is e to the minus 5t, and then the 4 and the minus 2t will give us this as the common factor which factors to that. So if I set this equal to 0, as Sarah, would you show the factoring process? Okay. So let's go back and pause for a minute there. Look at the thing that I'm underlining here, Taj, right? You can see that, okay? You can see that clearly, can you? Okay, so what's the common factor between both of those two things? What do you see that's common to those two? Write it down, or you can just unmute. I'm quite happy to hear from students. It's not that you always have to be using a chat for this, but it's up to you. What's the common factor? Give me all the common factors that you see between those two terms. So I wouldn't say 4, I would say 2 is part of the common factor, okay? So I'd say 2, because there's a 4 here and there's a 2 there. So I'd say 2, and then of course the e to the minus 0.5t. I'd say that is the common factor. Would you agree with me on that, Taj? Right? Okay. And then if I factor that out, I'm dividing this thing into both of these parts right here. What I'm going to get is the 2 and then the minus t, which is what I have right there. Are you okay with that now? Is that good now, Taj? Okay, great. All right, so get some practice with that whole factoring thing, because every time you have to find a derivative, that's what's going to be involved. All right? Well, let me take that back. When you have to find a maximum, that's what's going to be involved. You're going to set it to 0. Sarah made that point earlier on. And once you've set it to 0, if it's factored, then you can use the zero product law. So I've done that. And here it is. If I now look at this, the critical number occurs when x is equal to 2. Yeah, that makes sense, because 2 is what makes this thing become 0. Right? This can't be 0. We talked about that before. 2 times e to the minus 5 cannot give you a 0. So only 0 you can get is when x is equal to 2. I have x here. Of course, that should have been a t. All right? So if I go ahead and compare the slopes before and after the 2, it's positive on one side, negative on the other. All right? So if it's positive on one side, negative on the other, it does mean that there's a maximum. right? Remember that if you're going up, then you're going down. That must mean that you went to a maximum point, positive and negative. And that means that if you have a maximum at 2 weeks, which answers the part B of the question, what is the maximum number of squirrels present in the population? So now you know that 2 weeks into the experiment or to observation, I guess I should say, of these squirrels, 2 weeks and it hit a maximum. But the question is, how many squirrels do we have? And how do we answer that question? Come on, folks. I don't want to be the only one here. Plug the two into the original. Thank you, Richard. That's exactly what we're going to do. So plug two into the original to get 2.94. But please remember this is 294 because it says that P is a number of squirrels measured in hundreds. So multiply the 2.94 by 100. Thank you very much, Richard. Always happy to get that kind of input from the class. Sarah, Richard have come through in a big way. And Kushi and Taj as well. I'd like to hear from other people as well. So there you go. Nothing, particularly, I think, difficult about that question. Similar question, the net profit in dollars from the sale of a certain item is given by this formula. And you just have a formula, you just have an equation. X has to be greater than or equal to 1. So X can't be 0. If X is 0, then this whole function would disappear. The profit would be, I guess, 40 in that case, if X was 0. But X has to be greater than or equal to 1. Is the number of items sold in hundreds. All right? And the factory can produce 1,000 items per month. Determine the number of items that yields the maximum profit and what's the maximum profit. So we're going to take the same approach as we did for the previous question. Get our P of X function. And again, I'm going fairly quickly. I'm just simply using the function that was given to us, which is this right here, and going through the motions and thinking of this as a product. So it's 60 x squared as part of the product. And then the e to the minus 0.25x is the other part of the product. The 40 clearly is going to disappear when it's a constant. So that's clearly going to disappear when you take the derivative. So here is my derivative. And here is where I simplify the derivative sum. And here is where I factor again, Tash. Hopefully the factoring is becoming easier for you now, not just you, but everybody else. And I'm glad you asked the question, by the way. And again, if some of this is, you can't quite see that that's the factor immediately. If you slow down the video, pause the video and go through it on your own, then hopefully you will see why that represents the factor or factors of this function. Again, we're trying to get this to be equal to 0. So there you go. That critical number is at 8. All right. And we're going to go through the same process again. We're going to set up a little interval table. Minus infinity to 8, 8 to infinity. And then it's positive before and negative after, which means that the critical number is a maximum when you're producing, the profit is a maximum when you're producing 800 units. Okay? All right. And then we put the 8 back in to get the maximum profit. And it works out to be something in the region of $559. Well, $559.69. Okay? So that's hopefully fairly straightforward.